This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you enjoy The Future of Everything, please follow or subscribe wherever you listen to your podcasts. This will guarantee that you never miss an episode, and it'll help us grow. Today, Bill Mitch will tell us that the technologies for turning sewage into drinking water have improved greatly, and that purified water is coming your way soon. It may even win some taste tests against what you're drinking currently. It's the future of wastewater. Before we jump into this episode, a reminder that if you enjoy the podcast, please rate, review, and follow it. That will help us grow our listenership, and it'll make sure that you're never surprised by the future of anything. Many of us are lucky to have good access to clean drinking water. In fact, the separation of sewage from drinking water was a great public health intervention 2,000 or 3,000 years ago when our ancestors figured that out, and it led to much better population growth and health outcomes. But access to water should not be taken for granted. Even with global warming and the melting of the glaciers, not all the water that's being added to the ocean is easily turned into drinking water. One of the opportunities is to process sewage water into purified water that can then be delivered back to our faucets and our showers. Bill Mitch is a professor of civil and environmental engineering at Stanford University. He studies the chemical methods for water purification, as well as the engineering, sustainability, and public health issues necessary to create large-scale, safe water resources. Bill, your work in water purification is fascinating. Can we start with a basic review of what's in the water that you're trying to purify, and how good are we these days at getting it out?
Sure. Well, what we're looking at is reusing and purifying for potable reuse municipal wastewater, so essentially sewage. So what's in there? A little bit of everything. Whatever you pour down the drain eventually ends up in sewage.
Okay, very good. And how good are we now at getting out those components? And is it a separate kind of chemical process for each type of contaminant, or do they actually all get treated kind of the same?
Well, one of the difficulties we have to recognize is that we actually don't know all the things that are present in sewage, and we can't realistically measure them all. So just for your for fun, one thing you could try is next time you're taking a shower, look on the back of the shampoo bottle and look at what the ingredients are and see how many of them you conceivably can recognize, even if you are a chemist. Most of them I don't recognize.
That's right.
So we can't possibly measure the thousands of chemicals we pour down the drain. So the strategy is a little bit different. We don't target treatments to each individual chemical. We try broad-based sort of barrier treatments. It's called the multiple barrier effect. And so what we might do is say, all right, in California, we use reverse osmosis. Reverse osmosis is a membrane that theoretically, physically squeezes out everything but the water. So the organic contaminants are rejected into a concentrate stream that's the eventual waste product, whereas the pure water goes through the membrane. And so it's a broad-based chemical barrier, but certain chemicals we found, actually slip through RO membranes. So we follow that with a different kind of barrier, and that's called an advanced oxidation process, where we're generating radicals. And radicals are very potent oxidants, the same oxidants that people have heard about when you consume antioxidants to prevent oxidative damage in your body. We're looking at blueberries, that sort of thing. We're trying to go after radicals like hydroxyl radical. Well, in this treatment process, we're generating hydroxyl radical to ideally tear apart any of the chemicals, many of which we probably don't know, that might slip through this membrane. And so we have these kind of multiple barrier approaches, and there are different approaches in other states depending on their sort of local geographic problems that we can get into if you want.
So that's fascinating. So I never would have expected that. So before we move to the issue of the kind of heterogeneity of the systems, I'm imagining that there's a huge range of sizes of things that are in the water, and down to very small molecules that we don't like, up to, I'm sure, very big ones. And so you've described these two technologies. Do they do they get down to these very small molecules that that we might not want, that might be carcinogens or whatever, or are they limited in that respect?
Sure, great question. So The reverse osmosis membrane, ideally, like I mentioned, only lets through water, but it does let through some other molecules that are small in size. So the reason why we use reverse osmosis membranes in the first place is that they're very good at rejecting charged compounds. So these are the same membranes, for example, that are used for seawater desalination. So they're very good at rejecting sodium and chloride, essentially desalting the water. And there are also, of course, plenty of salts in municipal wastewater. So charged compounds, even of very small size, sodium's 23 grams per mole, can be rejected. But when you start to get to low molecular weight neutral compounds, some of them can slip through membranes. So originally, down in Southern California at some of the first full-scale plants for potable reuse of municipal wastewater, the only process was reverse osmosis. And then researchers discovered that certain molecules called nitrosamines can slip through RO membranes. So nitrosamines are some of the classic carcinogens that toxicologists have studied since the 1950s. That they show up in hot dogs, beer, cigarettes. So if you happen to go to the grocery store and you see a hot dog pack that says contains no nitrites, that's what they're trying to get rid of, are nitrosamines.
Gotcha.
So these form by a completely different pathway in municipal wastewater, but nonetheless, they were discovered, and they're very potent carcinogens. And so once those were discovered, that was the impetus to put in these advanced oxidation processes as the second barrier. And those, in the past several decades, have been, we look at the degree to which they can tear apart other low molecular weight neutral compounds that slip through reverse osmosis membranes. Some of those are things like industrial solvents, for example, chloroform, that kind of stuff.
So that story about Southern California, that goes right to the topic that you suggested, which is, first of all, there's a heterogeneity in the technologies that are used. And now I realize, and I guess it's obvious once you say it, that different locales will have different challenges based on the industries or the lifestyles or whatever. And so that might lead to the use of different technologies. So tell me a little bit about the variation. Now I'm thinking about things like sunscreen, which you're not going to find some places, but you might find a lot of it in other places, and a lot of other things. So tell me about that heterogeneity, and is it a problem, or is it actually a good thing?
Well, actually, it's a little. The heterogeneity derives from a little bit of a different reason, which is it tends to be inland versus coastal. So the challenge is everything that's rejected by a reverse osmosis membrane ends up in what they call a concentrate stream that contains all the organic contaminants, all the metals, everything else you don't want in the water, and discharge, and as well as the sodium and the chloride. And discharge of that concentrate can be problematic. So up till recently, it was considered fine in coastal areas to use reverse osmosis membranes because the ocean is relatively big and next door. So what if you discharge some salty water to that? But if you're
what could possibly go wrong?
Exactly. But if you're in an inland location like Colorado, discharge of that brine stream, the concentrate stream, becomes problematic because you might be desalting downstream people's drinking water supplies if you're, say, dumping it in the Colorado River.
Okay, so that's the big switch for you, is inland versus coastal. I did want to go a little bit. You mentioned the nitrosamines in cancer, and I know you've written a paper about emerging carcinogens, which obviously must be new molecules that we maybe didn't appreciate were problematic, but are, and even some links to bladder cancer. Can you tell us that story, and is it something that we will be hearing more about, things like this?
Sure. Well, what we've been trying to do is to figure out what are the toxicity drivers in the water. So the government tends to focus on a limited set of molecules that they monitor, and like I mentioned before, there are potentially thousands of chemicals present in sewage, so we can't possibly monitor them all. So we have to choose a few kind of sentinel compounds to monitor. And the question is whether the government's selection of molecules are the right ones. Because every time you target a select set of contaminants, you're making a choice about a particular treatment technology. And so you might be going after the ones the government cares about, but not necessarily doing a great job with other chemicals. So we want to make sure that we choose the right ones. So what we've been looking at over the past few years is whether the select compounds that the government focuses on really are the toxicity drivers in these waters. And we don't believe they necessarily are.
Okay, and you found it. I guess this was in China, if I remember correctly, that there were some wastewater compounds that were statistically associated with cancers. That were it was a novel association. Is that right?
Well, that was a study by a Chinese group that we were reviewing.
Okay.
But yes, they were looking at novel sets of kind of industrial contaminants that are in China that could affect their water supplies.
Great. Okay, so there's a lot of so thank you for this. Now we all kind of are up to speed on the general technologies. I wanted to ask about a number of things in terms of whether this technology, and I believe you believe it is, ready for prime time. So what are the energy costs? Because obviously everybody loves the idea of pure water. That's hard to argue against that. It's right next to motherhood, probably. But it comes at a cost, I'm sure. Both the I guess the knock-on effects of having a lot of chemicals to treat the chemicals, and also energy. So where are we now in the energy efficiency of purification?
So reverse osmosis is an energy-intensive process, but the key detail is relative to alternative choices of water supply, namely seawater desalination. It's about half the cost. And that's because of the osmotic pressure associated with sewage is a lot lower than the osmotic pressure of seawater. So it takes less energy to push that water through the reverse osmosis membrane. So that's one thing. But another major consideration for utilities is access to the water itself. So certainly if you're in an inland area, you have no access to seawater. But even in coastal areas, it's rights to water. So it should be no surprise in places like California that people are constantly fighting over access to water supplies. So we worry about whether the pristine water supplies where we have historically gotten our water will be available due to drought, but also due to competition from other entities. So witness the sort of fights between states over rights to the Colorado River water.
Yes.
But so when we look at something like municipal sewage, it's a reliable supply of water that the municipality controls. And the flows approximately match what you need. What goes out the sewer is about what you needed to go in the first place to your house.
Right. It's not quite a closed loop, but you could imagine a closed loop.
Yes, exactly. And it is that's when you speak about closed loop, that's an excellent point because that's essentially what's going on in our field. Is historically we had the once through motif. We would get water from distant sources, Hetch Hetchy Reservoir up in Yosemite, use it once, clean it up just enough so you could throw it out in the bay in a safe fashion. And that's perhaps no longer tenable given the sort of droughts we've experienced over the past few years. And so now we're moving to a circular water cycle. So there will be some makeup, no doubt, from pristine water supplies, but we're increasingly looking at gathering the water, using it, and reusing it in a potable fashion. But beyond just extracting the water, looking at sewage as a source of vital resources. So some of the things that we're also looking at elsewhere on the Stanford campus, along with collaborators in my department, is you have dissolved organic matter, no surprise, in sewage. And historically, what we would do with that is oxidize that dissolved organic carbon to CO2 using bacteria, pumping in oxygen. Oxygen's poorly soluble in water, so that's a very energy-intensive process. Instead, could you ferment those organics, make methane, and harvest that to run the wastewater plant? So on the Stanford campus, there's a...
Wow, so I'm just going to stop you because that's a really exciting idea. So the old way was use energy to get oxygen in there, grow bacteria, have the bacteria basically eat and transform the organic waste. But now there's the idea of harvesting the waste and not letting the methane become a greenhouse gas. Obviously, this would be very controlled, so you could just use it as fuel to process the other water.
And so harvest the energy from and run essentially an electricity generation plant on site to help run the plant.
Have these been prototyped? Do they look like they'll work?
Well, exactly. So on the Stanford campus, there's a research center called the Codiga Center where we have a pilot scale facility that is scalping sewage from the campus sewer, and is running this anaerobic process, generating methane. And we're not currently, we don't have an electricity generation plant, but we're monitoring methane yields, and we can model how much would form.
Right.
Redwood City, or what's called Silicon Valley Clean Water, it's sort of the wastewater treatment plant that services Redwood City, Menlo Park, and those sorts of areas on the peninsula, has an even larger pilot scale facility where we're helping operate, and we're taking the methane out of that wastewater, and current calculations indicate that for the first time, this wastewater plant is energy positive. So instead of putting energy in to just clean up the wastewater, this would just be for disposal to the bay, but that we can now run it as an energy generation system.
This is The Future of Everything with Russ Altman. More with Bill Mitch next. Welcome back to The Future of Everything. I'm your host, Russ Altman, and I'm speaking with Bill Mitch of Stanford University. In the last segment, Bill told us about advances in technology for turning sewage into drinking water, and he ended with these intriguing ideas about gathering energy from the sewage water so that the power for purification comes from the water itself. In this next segment, he'll tell us about other things that can be pulled from wastewater, and he'll also talk about the challenge of public acceptance of drinking water that used to be sewage. At the end of the last segment, Bill, you told us about this, what you called anaerobic style, where instead of having bacteria use oxygen to break down these contaminants, you're actually using different processes to create methane, which can be used to actually fuel. So is that the main thing you're getting out, or are there other things that you can also extract from the wastewater?
Well, so we can extract the water through the reverse osmosis membrane. We can extract energy in the fashion we were just talking about, fermenting the organics and then harvesting the methane. And then the third thing that people are targeting is harvesting nutrients, so nitrogen and phosphorus out of the wastewater. So the traditional way farmers get nitrogen is through the Haber-Bosch process, which is very energy intensive, essentially breaking the triple bond in nitrogen gas to make ammonia. We use it once, it goes out the wastewater plant and fuels algae blooms in places like the bay. So a lot of the utilities surrounding the bay are awaiting regulations on the discharge of ammonia to the bay. And how are they going to deal with that? The conventional way of dealing with that is putting a lot of energy into the system to oxidize that ammonia to nitrate, and then a separate process to reduce it back to nitrogen gas. But a very expensive process overall.
Yes, it sounds like several chemical transformations, and some of those chemicals are not your favorite, safest chemicals, it sounds like.
Well, these are all, for the most part, biological processes that are doing these transformations of the nitrogen, but it still involves a lot of energy, and there are some associated chemicals as for part of these processes. But the overall scheme, though, is that we're putting energy in the front end to make the ammonia, using that ammonia once, and then putting in a lot of energy at the back end just to safely dispose of this water to the bay. So could we instead harvest the ammonia, which is ultimately what the farmers want, directly from the wastewater? And here's where some of the synergies come in, because ammonia is a low molecular weight charged substance, kind of like sodium, ammonium. So as it hits the RO membrane, it's rejected into this concentrate stream. So that when we conduct reverse osmosis for wastewater reuse, we essentially pull out about 6/7 or about 85% of the water comes out as clean water, but all the contaminants are now crunched down into something that's about 1/7 the volume. So we get a 7-fold concentration factor, essentially, of the ammonia for free while generating the water.
Enriching.
Yeah. Which makes it much better to essentially harvest these nutrients.
Yes, I was going to say, is it then relatively straightforward to harvest the ammonia and deliver it to the farmers and whatnot?
Well, that is actually the scheme people are working on now. Not necessarily just me, but other people on campus are looking at different technologies to extract that ammonia. It's certainly not even at pilot and definitely not at full scale yet. These are mostly lab scale schemes. So we can take advantage of the concentration, but how do you then extract and purify the ammonia from all the other contaminants that are in that concentrate stream? So to kind of summarize, for the circular water economy, we're already at full scale for extracting the water. These plants are prevalent throughout Southern California, and one's under development right now at the Palo Alto wastewater plant. So it'll be coming soon to Stanford, essentially, becoming part of the Stanford water supply ultimately. And for the sort of harvesting methane, we're at pilot scale in places like Redwood City and on the campus. But harvesting the nutrients is going to be further down the road, shall we say.
Gotcha. Is it a similar story for, you mentioned phosphates as well?
Phosphates are also of interest. That the immediate need from certainly in utilities around here is nitrogen removal, because there's a regulatory impetus for them to have to remove the nitrogen, putting all this energy in. There are no, at least in this area, measures on the part of the regulators to require phosphorus removal. So there's less of a regulatory driver to find an alternative. But ultimately, yes, we can't keep harvesting phosphorus or mining phosphorus in Florida forever.
Great. So I wanted to go to the issue of public acceptance of these technologies. You know, I'm sure that you've come up against this. People talk about recycled water and they get nervous, especially, you know, they're fine using it perhaps for watering their plants, and they're fine with a bunch of uses. But then when you tell them that it's going to be part of the drinking supply, my guess is that people start asking questions. And so tell me about where we are with that. Have you experienced that? And how receptive are people to the arguments in favor of this kind of closed loop that we've been talking about?
Sure. I think there's been a sea change in people's attitudes in the past couple of decades. So when I was in grad school back in 2000, there was a full-scale plant that Dublin San Ramon, an entity near us across the bay, had developed for potable reuse. And they never turned it on because of the public, the media got a hold of it, and people got afraid of essentially drinking toilet water. A similar story happened down in San Diego about 2 decades ago. They were planning to put in a full-scale potable reuse and eventually had to shelve it due to consumer concerns. That's changing, and now San Diego is putting in one of the largest potable reuse facilities in California, and it eventually will supply about 50% of San Diego's water supply.
So let me ask, sorry to interrupt, what changed? Is it the technology that changed, or the communication and consultation plan with the community?
Primarily the latter. So the San Diego and other entities that have engaged in potable reuse have put a lot more effort into the public relations campaign. So they've realized it takes a decade or more to sort of bring in school. So what they typically do is we'll build a demonstration scale facility for the technology where they can bring people in, school groups, etc., and have them walk through the plant and notice that it's not a filthy conventional wastewater plant, but looks like a drinking water facility. They can see the product water. In some cases down in, say, Orange County, they've actually bottled the water and they can sell it.
You can have a tasting room. It'll be like going to a brewery.
Exactly. So they have those already down in Southern California. And our own Valley Water in the San Jose area has one of these demonstration scale facilities that tour groups go through, etc. The other thing is they've brought on board other entities that can benefit from the potable or the whole circular water cycle. So, for example, Surf Riders Foundation. People who surf traditionally are surfing off the coast where there might be a wastewater outfall. So, and to them, it's having reuse of various kinds. It is nice because it diverts contaminants away from their surfing areas. Similarly, for various sort of ecosystem groups, Nature Conservancy, that sort of thing, because if you're recycling the water, there's a lower demand on the pristine water supplies, and so there's more water for fish, etc. So looking at these kind of multiple benefits, plus the more obvious driver of drought in most people's minds have realized that, hey, that plus seeing some of these full-scale facilities that have been in operation now for decades in Southern California and not hearing disaster stories of people getting sick and that sort of thing, people have learned to accept this.
So this is great. And a couple of quick questions to follow up, because you gave a lot of interesting news there. First of all, when you look back at these plants from 20 years ago or 30 years ago, was the technology, was it actually going to be fine? In other words, if those hadn't been stopped by the public, would everything probably have gone well? Or in retrospect, yeah, that technology wasn't ready? I'm just wondering about that kind of post hoc analysis.
They have not changed dramatically in the past 2 decades. The technology is
Okay.
essentially the same. And one of the things we did recently was to sort of address some of these potential consumer concerns, is to say, to what extent is the effluent water from these plants, how does it compare in terms of toxicity to our conventional drinking water supplies?
Right.
Because from a utility point of view, it's the opposite of what the consumers are thinking. Because they're saying, well, in your conventional water supply, there are for sure contaminants, and we're putting in much less sophisticated technologies to clean it up. What we're doing at these potable reuse facilities is essentially making deionized water. So perhaps the water is actually of higher quality. We wanted to sort of compare side by side conventional drinking water and potable reuse waters and see how they compared with at least one toxicity assay. And what we found is that the reverse osmosis treated waters were of higher quality than our conventional surface waters. So waters you might get from a reservoir, for example, and comparable in quality to what you might get from a groundwater supply, which is traditionally higher quality than what you get from surface water because there's less organics and other things in groundwater.
So that's fantastic. And I guess one kind of random question that I wanted to ask is, because I know you've written a little bit about this, which is this: sometimes when we drink water, especially if we're traveling to a new area, there can be a chlorinated taste to it. And I wanted to ask, and this is just a basic question: should I feel reassured by that chlorinated taste, or is that a red flag?
That's an interesting question. So oftentimes what you are tasting is a difference between the final disinfectants in your water. So historically, people use chlorine, essentially Clorox bleach, and that doesn't have much taste itself, but it interacts with organic matter and makes products like chloroform that are volatile, and so they can go up your nose and you can smell it, which is also part of taste. But in areas like the Bay Area, people use chloramines as the final disinfectant. So essentially you inject ammonia, it reacts with the chlorine and makes a less reactive oxidant that's still a disinfectant called chloramines. But they tend to be more volatile, so you can taste them more, essentially.
Gotcha. Gotcha.
Again, nose and mouth.
And the final question I want to ask is: I've had other guests on this podcast talking about how it might, in some point, be useful to have separate infrastructures for potable water versus water that's used for other purposes because of the expense and challenges. And I'm wondering, given our discussion about the closed loop, do you see that as part of the future, or is that just like kind of a logistical nightmare that won't likely happen?
It's actually, in most cases, it's the latter. So in the early days of reuse, due to consumer concerns, most of the larger utilities, such as Valley Water down in San Jose, installed separate infrastructure. What they call, when you see purple pipes, it's the non-potable reuse water, the water used to irrigate golf courses. But the cost of the treatment upgrade to make potable quality water is a drop in the bucket compared to the cost of installing separate pipelines. So most entities, including Valley Water, are moving towards potable reuse as a more efficient system. That doesn't mean they're going to shut down the purple pipe system, because once you have the infrastructure, it is cheaper to treat the water in that fashion.
Cost.
But for the most part, they're moving towards potable reuse.
Excellent. Thanks to Bill Mitch. That was the future of wastewater. You have been listening to the Future of Everything podcast with Russ Altman. If you enjoy the podcast, please consider subscribing or following it so you will receive news of new episodes and never be surprised by the future. Tell your friends about the podcast too, and definitely rate and review it. We have more than 200 episodes in the archives, and you might want to check those out because there's a lot of good stuff. You can connect with me on Twitter at RB Altman and with Stanford Engineering at Stanford ENG.